Welcome to the pre-seminar of Combinatorics. And today we're happy to have Isabelle Shankar from UC Berkeley, and she's going to talk about Symmetry Adapted Gram Spectrahedron. And this is the pre-seminar that it's from 3:30 to 4. Feel free to ask any questions during the talk.
Yeah, so thanks for having me, first of all. So I won't actually get to talking about Symmetry Adapted Gram Spectrahedron in this pre-seminar, but what I do plan on going over is some basics about sums of squares, and then a little bit into symmetric polynomials as sums of squares. So there's some interesting things that we can do to the sums of squares problem if you're presented with a symmetric polynomial. So I'll be touching on those two things in this pre-seminar, and then apologies for those of you who are here and also going to be in the main talk. I'll probably be repeating myself a little bit there too, so you'll see this all again there. So let me start with a bit of motivation. Why would we be interested in sums of squares? Well, it comes from polynomial optimization. Right, so here's a basic polynomial optimization problem, a POP. We're taking the inf of some polynomial p over Rn. And this is an unconstrained polynomial optimization problem even, so looking over all of Rn. And even this unconstrained problem is NP-hard. Right, so we probably want to think about ways to solve this, some easier ways to solve this kind of a problem. So let me reformulate the problem a little bit. Instead of taking the inf, we're going to take now the sup over real numbers gamma, such that p is greater than or equal to gamma. And then I'm just going to subtract over the gamma. And so now we're looking at trying to prove non-negativity of some polynomial p minus gamma, which, still hard, but this is what we're going to relax to a sums of squares problem. So rather than trying to prove non-negativity, I'm interested in showing that this polynomial p minus gamma is a sum of squares, SOS. And what I specifically mean with sums of squares in this case is a sum of polynomials squared, right? So you're going to have some sum, maybe QIs, QI squared, and then the QIs themselves have to be polynomials. Now, hopefully it's clear that if we find a sums of squares decomposition for a polynomial, or if we prove that it's a sum of squares, then of course it's non-negative. It's worth noting, though, that it is in fact a relaxation. It's not perfect. There are non-negative polynomials which are not sums of squares, but in practice it's actually been shown to be quite effective.
Is that already true in two variables, or how many variables do you need to get to that?
For there to be a difference?
Mm-hmm.
Yeah, so Hilbert actually proved that in the case, so I'm gonna talk about homogeneous polynomials. Everything in this will be homogeneous. So in the homogeneous case, yeah, in two variables, they're still the same. So the cone of positive positive polynomials and sums of squares polynomials are the same. I think there's two other cases, and I always sort of forget. I think if the degree, so quadratics, degree 2 polynomials, 2 variables, and then the third case is 3 variables and degree 4 polynomials. And any other cases, so all other cases, in terms of number of variables and degree, the cones, there's the SOS cone is strictly contained in the positive cone. Yep. Cool, so let's talk a little bit about sums of squares. Why would this be a good relaxation? How does it actually make it easier? Well, let's start with a polynomial p. Again, I'm going to say it's homogeneous, by which I mean the degree of each term in the polynomial is the same, and specifically of degree 2d, right? So we always need an even degree. Then there's this really important fact, and this is sort of why we would do the sums of squares relaxation. A polynomial p is a sum of squares if and only if we can write it in this form here, this quadratic with the x bracket vector, where q, or what would I call it, the Gram matrix is positive semi-definite. And so that's what this notation over here means. So let me say that again. If we can find a positive semi-definite matrix Q such that we can write our polynomial in this form, that would certify that it's a sum of squares. So this is an if and only if statement. The X bracket is actually a monomial vector. It's a vector of all monomials of degree D, right? So we started with a polynomial of degree 2D, and then this X bracket is all degree D monomials. And so what this means, right, what we're actually boiling down the problem to is a semi-definite program, because we're searching over the cone of positive semi-definite matrices subject to these linear constraints, where we have P alpha as the coefficients to the polynomial P is equal to some linear combination of the unknown entries of Q, of our matrix Q. And typically for a semi-definite program, the feasible region is called a spectrahedron. And in this case, when we're the semi-definite program that comes from a sums of squares problem, the spectrahedron is called a Gram spectrahedron. Yeah, so any questions before I move on? And I can't see the chat, so if there's any questions in the chat, if someone could shout them out, that would be very helpful. Okay, well, I actually have an example to go over. So if there's questions, maybe some things will be clarified here. So here's a polynomial. I claim that 5x squared minus 2xy plus 2y squared is a sum of squares. So according to the fact that we saw a moment ago, I'm going to try to write this polynomial in that x bracket q x bracket form, right? So here's my degree 1 monomials, because we started with degree 2 polynomial. And so we're going to have this 2 by 2 matrix, and we're going to search over all positive semi-definite matrices such that this equation holds when we expand it out. So the top left corner of the matrix corresponds to the x squared term, so that's going to have to be 5. The bottom right will have to be 2, since it corresponds to the y squared term. And then if we want the matrix to be positive semi-definite, we need it to be symmetric. So the last 2 entries are going to be the same number, and they have to sum to the xy term. So we're going to put negative 1s there. And indeed, this matrix is positive semi-definite. You can check, for example, in many ways, but for example, the principal minors, so the 2 diagonal entries in the determinant, are all non-negative. So according to my theorem, or my fact from earlier, I have now certified for all of you that this polynomial, in fact, is a sum of squares. Now, this might not be satisfactory to everyone, because we didn't actually write it as a sum of squares, right? We don't know what the decomposition is. So the key to that if and only if statement really is the fact that this is positive semi-definite if and only if it can be factored into some matrix U transpose U. So that's the key to the if and only if statement earlier. So I'm going to choose my favorite factorization. There are many and they're not unique. So here's my factorization of this matrix, which then informs, kind of gives me the breakdown of how the sums of squares decomposition will show up, right? So we'll have this negative 2x plus y is one square, and then x plus y is the other square. Something to note before I move on is that we have 2 squares here. And that's exactly because this matrix in here, our Gram matrix, is rank 2. So the rank of the Gram matrix that you get will correspond directly to the number of squares you have in your sums of squares decomposition. So that's kind of a nice thing. And so we've become interested in sort of what ranks you get for different polynomials. And I believe I'll be going on to symmetric polynomials after this. So before I do that, are there any questions?
So I see that these decompositions aren't unique. It's like when I look at that polynomial, the most obvious one that comes to mind is 4x squared plus x minus y squared plus y squared, but that one's got 3, so this one's smaller.
Mm-hmm. Yeah, definitely. They aren't unique. Yeah, I mean, even in this case, because we're in a homogeneous case, I'm actually, so if we didn't have a homogeneous polynomial, or even if we did, I suppose, we can expand the size of the problem by including all degree D monomials and down. So degree D equal to D or less than D. And so we can get then, we have a longer vector, which means we have more, a bigger gram matrix, right? Which means we can have higher rank options, right? So yeah, there's definitely not necessarily uniqueness here in the decomposition.
Oh, so the degree, so like the number of terms in the minimal one is not the rank. It's that was just a coincidence that it's some sort of
yeah, so minimal
polynomial
rank will give you
coefficient.
the minimal number of squares, right?
Right, I mean,
so,
it's not necessarily the degree. It's not. It's the fact that it's a degree 2 polynomial is just a coincidence, right?
Oh yeah, yeah. Yep. Other
So
questions?
does this imply that if you have a sum of squares in n invariates, then you can write that as a sum of at most n squares?
Sorry, could you ask the question again?
So if you have n invariates and you have some sum of squares, can you rewrite that as a sum of at most n squares then from this?
I'm not sure. Sorry, if you have n invariants?
Or
what do you mean?
n variables.
Oh, I see. No, you will have, yeah, I'm actually not sure if you can always, I mean, the monomial vector, right? So I'm not sure if this will answer your question, but the monomial vector, in this case, we had a degree 2 polynomial, right? So we only had degree 1 monomials. But in a bigger example, we will want all degree D monomials, right? So that'll be more than just the number of variables. So we could have a full rank matrix, or at least a R-1 rank matrix, which would then give you a more squares. But yeah, I'm not sure if maybe that is an upper bound. I'm actually not sure for like the lowest rank option. Cool. Well, I'm gonna keep going to symmetric polynomials as sums of squares. So this is really what I'm interested in, is writing symmetric polynomials as sums of squares. And I'll go into this a bit more in the main talk, but I kind of wanted to touch on it here to give anyone who hasn't seen this material a chance to sort of just see it for the first time and digest a little bit before the main talk. Right, so we have symmetric polynomials. Suppose you give me a symmetric polynomial of degree 2D. Then we have some SN action on that, but I'm actually interested in the SN action on degree D polynomials. So here, and I'm just talking about the usual SN action of permuting the variables. So kind of think about it as we're acting on that monomial vector instead of the space of the polynomials that you all gave me. So this has a matrix representation. I'm going to call that D sigma. And that actually induces a representation on the space of symmetric matrices by conjugation, right? So we can act on a symmetric matrix X by multiplying on the left by D sigma transpose and on the right by D sigma. With this action, it has some fixed point subspace. So the space of symmetric matrices that are fixed by that action. And it turns out, so if you want to read this whole thing, you're welcome to. But essentially, what this theorem by Gutterman and Perlot tells us is if we have an invariant SDP, semi-definite program, then rather than looking at the entire PSD cone, we can restrict to the fixed point subspace. So we can restrict to matrices, symmetric matrices X that are fixed by this action. And that will give us, in fact, an optimal solution. So that's really nice. And the way we apply this is for symmetric polynomials, the SDP, the semi-definite program that we get from trying to write that polynomial as a sum of squares, is in fact an invariant SDP. So we can apply this theorem and instead of searching over the entire PSD cone, we can search for a Gram matrix that commutes with our representation. So I'll do an example. Here is a degree 4 symmetric polynomial in 2 variables. Again, I'm interested in the SN action on the space of degree 2 polynomials in 2 variables. So that has that's spanned by these 3 monomials. And that has made this as its matrix representation, right? So the identity element is, of course, the identity matrix, and then the 1, 2 element has ones on the anti-diagonal. So what the theorem is telling us is that instead of looking over all matrices, symmetric matrices X, we can restrict to the ones that commute with this representation. Of course, everything commutes with the identity matrix, but we can forcing our X or our Q matrix really to commute with this matrix will reduce the problem size. So let's set it up the way we normally would. So the fact about sums of squares tells us that if we write our polynomial in this form, so here's our Q matrix, our Gram matrix, and here's our monomial vector of all degree D monomials. Instead of looking at all matrices, 3 by 3 symmetric matrices, we can look at the ones that commute with our D1, 2 matrix. And what that actually ends up doing is it tells us that Q11, excuse me, is equal to Q33, and Q12 is equal to Q23. So why this is important is exactly this. We go from a problem, a semi-definite program with 6 unknowns to 4. And in higher, in bigger problems, the reduction gets to be quite great. So that's a huge improvement for the sums of squares problem for symmetric polynomials. And it turns out there's one more thing we can do to this sums of squares problem in the symmetric polynomial case to make it a little bit easier. So that's what I'll be talking about next, and I'll elaborate a bit more on this in the main talk. So there's definitely some representation theory playing around in the background here. And I won't really go too much into the detail of it. I'll talk a little bit more about it in the main talk. But just know that the matrix representation, D sigma, can be block diagonalized. It always can. And you can calculate the change of basis matrix T such that it block diagonalizes this representation matrix, these representation matrices, and such that T is orthogonal, which is going to be pretty important in a second. So what do we use this for? Well, it not only does it block diagonalize our matrix representation D sigma, it actually turns out that once we've done that original reduction where our Q matrix commutes with our representation matrices, it turns out that T also block diagonalizes our Q matrix, our Gram matrix. So now how do we use this fact in our actual problem? Well, we start with our polynomial equal to this form here, right? This is what we were hoping for. And by Q here, I mean the reduced version from earlier. Now, since we calculated T to be orthogonal, we can insert it in since TT transpose is in fact the identity matrix. And then now we can see where this block diagonalized matrix comes into play. So here we have the block diagonalized matrix, and we still have a sort of quadratic form with some sort of a vector of polynomials. It's still a basis of the space of degree D polynomials. It's just a different basis now, right? And this is what's called a symmetry adapted basis. So essentially what we're doing is changing the monomial vector to, again, something called a symmetry adapted basis in order to block diagonalize our Q matrix. Now, why would we want to block diagonalize our Q matrix? Well, it turns out that a matrix is positive semidefinite. Such a matrix is positive semidefinite if and only if its blocks are positive semidefinite. So we've sort of, rather than having one big matrix to try to run a semidefinite program on, we've broken it up into smaller pieces.
Could I ask a quick question about this? Sure. So when you block diagonalize, is there anything we can say about the size of each block?
Absolutely, yes. I have a slide on that in the main talk. But let me actually maybe mention it. So inside of these blocks are more blocks. So each qi tilde has some blocks qi, and the size of those blocks is actually equal to the multiplicity of. So each one's actually associated to an irrep. And so, of course, that irrep has some multiplicity and some dimension. The number of copies of the QIs is equal to the multiplicity, and the size of the QIs is equal to the dimension. And I'll if that was a little quick, I'll say it again in the main talk. But that's what ends up happening, which is quite nice. Other questions? So let's go back to our example. I'm going to end by showing you the block diagonalized form of this, essentially. So there's some change of basis matrix T, which again, in this case, maybe let me go back. So there's some change of basis matrix T that block diagonalizes this matrix representation, right? And again, it's orthogonal. There's algorithms for calculating it. And now that we have this restricted semi-definite program, we can block diagonalize that, and we get this 2 by 2 block here, and this 1 by 1 block. And I won't solve it. If any of you get bored during the talk, you're welcome to try to solve this. Essentially, you use this equation up here, and equate coefficients with the actual polynomial that you have to get your affine subspace in the QIJs. And then once you plug that in here, you'll find that there's actually just one solution. So it actually made it quite easier. It's a little easier than if you were to just try to solve this problem up here. But yeah, that's essentially what I have. Any questions?
Can you go back one slide real quick?
Yeah, of course.
So the symmetry adjusted X bracket vectors, do we have a handle on what exactly those are going to look like? They're still going to be polynomials, but what else can we say about like the order or the degree?
Yeah, so they will be, essentially they will be a basis for the irreps. Right, so we have we have this S in action on the space of degree D polynomials and n variables, and that has some decomposition into irreducibles of Sn with some multiplicity, right? So in this case, for example, we actually have the trivial irrep and then the alternating irrep, and the trivial irrep is has a multiplicity of 2, and so you will get 2 polynomials that are that form a basis for each one of those copies of the irrep, of the trivial irrep. So in this case, actually, we would get, I think, I don't know, I can't remember in what order, but one of the polynomials will be x1 squared x2 plus x2 squared. The other one will be x1 x2, and those give you the two copies of the irrep, right? Of the trivial irrep. And then the last polynomial, the third polynomial, will be a basis for the alternating irrep, which does appear with the multiplicity 1 in this case. Yeah, so that's actually really quite nice as well. We get these sort of bases for the irrep. Any other clarifying questions too? If I went too fast anywhere, I'm happy to go back.
Well, if there's no more questions, let's unmute ourselves and thanks, speaker.
Thank you.
Thank you for the nice introduction to SOS.